Hi folks, we are on the Unit 1 Day 7 lesson, and today we're going to look at just kind of an introduction to algebraic vectors. Now most of the vectors that you have seen in the early part of this unit were the geometric vectors. We just kind of briefly talked about the algebraic. In the next 3 lessons though, we're going to get much deeper into the idea of algebraic vectors and learn how to plot them and analyze them in 2 dimensions and 3 dimensions. So just to recall, this we covered early on in the very first day on vectors. Algebraic vectors are vectors placed on the coordinate plane. Now that assumes that those algebraic vectors take up 2 dimensions and are two-dimensional in a two-dimensional space, which as we'll see is not always the case, but it's the easiest one to kind of conceptualize because we're really good at the XY coordinate plane by now. So remember we talked about R2 being the definition of our regular XY coordinate plane, and that's the set of all pairs of numbers x and y such that x and y are both in the real number system. So really essentially what this is, it's every point on the xy axis, on the regular Cartesian plane that you guys have been working with for years. And when we describe an algebraic vector on that plane, we give it a coordinate, and that coordinate is where the head of the vector would be if the tail of the vector was oriented at the origin. So if you start at the origin and travel along the path of this vector, where do you end up? So this vector r, for instance, goes directly up 3 units. So it's given as 0, 3. Now remember the really important thing, and I think this is at least the 3rd or 4th time, vectors have 2 things. Vectors have magnitude and direction. We say that all the time. You have to remember both the magnitude and the direction solving for a vector, but they do not have position. So they don't have a specific location in space. We kind of give them this arbitrary location as starting at the origin, but this vector r, if you drew it, and I think I actually did this the first time we had this slide as well in the video earlier, if we drew that r over there, it's the exact same vector. If we go down here and draw the r, as long as the magnitude and the direction are equal, that vector is the same. The location is totally arbitrary, but to give ourselves a good notation with how to describe algebraic vectors, if we start them at the origin, then it's really nice and easy to define them as where they end. If you start at the origin and follow that vector, where does it end? So that just gives us a nice easy notation. And of course that negative r vector is shown there as well. So in this case, we've got vector v. This is a vector in R2, so this is on a two-dimensional space and the xy plane, and it locates that point in space. It says that it locates the point that's 4, 3 from the origin. So if you start with the tail of the vector at the origin, the head of that vector will be at the point 4, 3. So that goes 4 in the x direction, 3 in the y direction. Remember that we can write this as a starting and ending, like vector AB that we saw a lot of. So this would be vector OP. O means the origin, and P is the point where the vector ends. So this goes from the origin to point 4, 3. So if you have a vector in algebraic form and you've written it as the coordinate there, and you wanted to write it with 2 letters describing the vector, you'd always have an O first for the origin. And this is just a diagram. Obviously, we've gone to the point 4, 3, and we're starting at the origin. So that's vector OP, which is given by 4, 3. You do have to kind of be clear. Obviously, it can be kind of hard to tell whether something is a point or a vector. And there is kind of a lot of overlap in what that means. But if we're talking about vectors, that 4, 3 is not a point. We know that if it's equal to a vector, or using a vector symbol there, that we're talking about not just the point 4, 3, but the vector from the origin to that point. So we've been kind of talking about the XY plane sort of for years, but quite a bit in this course, and just kind of assuming that we know what it is. But let's just get into a little bit more definitions here. So what exactly is a plane? We talk about the XY plane in R2, and that's a flat surface that extends forever in all directions. It does not have any thickness, because that would be a 3rd dimension. So it's a 2-dimensional space, and each point on the plane can be located using an X and Y coordinate. So that's obviously kind of our definition of the XY plane. The XY plane that we are really accustomed to, though, is not the only plane out there. It's the one that we use a lot in kind of especially early math, but planes can be any 2-dimensional surface that extends forever in all directions. And we're going to learn a lot more about planes as we get into Unit 3 in this course. For now, though, what we want to do is kind of extend our idea of planes into 3 dimensions. So we're going to extend R2 into what's called R3. So we're going to start talking about 3-dimensional space, not just our 2-dimensional plane, but we're going to add a 3rd axis. So instead of the XY axis defining a flat 2-dimensional plane, we're going to add a 3rd axis, Z, that will define 3-dimensional space. These axes are all at right angles to each other, which is very convenient, and are perpendicular. If you want to take a look in your textbook, this shows what's called a right-handed system, and it's kind of, I'll see if I can get my hand under the camera here. It kind of shows us where the X, Y, and Z axis are compared to each other using your right hand. Sometimes people get mixed up on which side would be the positive or negative, and really this is all fairly abstract and arbitrary, but it does really help if we standardize the way that we write it. Just like if you probably when you guys were in like grade 8 or grade 9, a lot of my grade 9 say, which one goes up and down again? And you have to say, oh, that's the Y. It is arbitrary that we call that one Y and the other one X, but it makes life a lot easier. And just like that, we want to be consistent with our 3 axes, and it's a little bit harder to draw. So this is a diagram. This is a pretty good representation, and I really kind of like how it's color-coded here. And this shows the way that we're going to consider the X, Y, and Z axes. So basically what we've done, and it does sort of throw people for a loop, and I don't have a good description as to why things kind of switched around, but it's sort of like if we took the regular, say like X and Y, and we kind of spin them so we're looking at them in kind of giving them some perspective and adding in a 3rd, and this is going to probably make my camera go nuts, adding in a 3rd dimension, Z, coming up and down out of the page. So So it is kind of arbitrary. I know people are saying, but this used to be y. Why is y kind of tipped over there? They're trying to show you that the x and y are kind of what was originally flat on the page, and make it look as if the z is coming out of the page to give you that third dimension. Now, whether or not that actually works for you, kind of different people, I think, squint and turn their heads a bit differently to see this, but this is the, probably the best example of how we're going to be plotting points and looking at space in 3 dimensions. And obviously drawing 3-dimensional space on a 2-dimensional page is a bit of a challenge, and we're going to be working through that. This one is rotated a little bit. The other one that we had kind of had the X swung a bit this way and the Y swung a bit that way. But I do like this representation because it kind of shows you like this graph paper-ish grid, that's what we used to know about, and now we've pulled it out and added that third dimension vertically up and down from the XY axis by adding that Z axis to give us like an infinite up and down 3-dimensional space from our original 2D plane. So in these, each pair of axes is going to determine a plane, and I may switch back to the first diagram there. The XY axes determine the XY plane. So you can see here we've got kind of a little bit shaded in. This is our old XY plane. That's our nice friendly XY plane that we were really used to. But we also could look at the XZ axis and say that that's the XZ plane. So this plane here between the red and the blue, those ones are going to define a plane that is perpendicular to that Y, perpendicular to the XY plane. And similarly, the YZ axes will define a plane. So if we looked at the plane between the blue and the green and across the back there in this diagram, that will also define a plane in this 3-dimensional space. So to plot points here, it is going to be a little bit complicated. We're going to get into this a little bit later in the example. The points are going to basically, just like what we did in 2 dimensions when you guys were in probably grade 7 or grade 8 learning how to plot points, you would move along the X to wherever the X value was, and then move up and down along the Y axis to wherever the Y value was. But now we're adding in a third step. We have to move along the Z axis to the Z coordinate. So again, I'm going to kind of flip back to that earlier slide. So we're going to move along the X to where the X is, along the Y to where the Y is, and along the Z to where the Z is, and kind of where they all come together. If you can kind of visualize, it looks like kind of a rectangular prism that we have to go this far in the X direction, this far in the Y, and that far in the Z direction to come to your point P. So we're going to look at how to graph those later in the lesson. The last piece, this kind of goes a little bit back into our 2-dimensional vectors. If we talk about components of vectors, we can, from given a magnitude of a vector and the angle that the vector makes, we can find how far in the X direction and how far in the Y direction that goes. So we can kind of go back and forth. If we know the X and Y components, we can figure out the magnitude of the vector and the angle that it makes. And likewise, if we know the angle, we can figure out the XY components just using SOHCAHTOA. So if you see something about components of vectors, those are 2 vectors typically in the X and Y directions that can be added together to come up with the total sum vector. So we could, for instance, want to find components, and we will get into this later in Unit 2 when we're looking at forces. If you were applying a force at this angle, we could figure out how much of the force is going in the x direction and how much is going in the y direction. So that might be horizontal and vertical. It might be, if we were talking instead of forces, it might be something that was, say for instance, a velocity, how much of your velocity is north and how much is east, that sort of thing. But again, we're just going to take this value and figure out the theta in here, and take my total vector for the force of 200 newtons and just use SOHCAHTOA that we can figure out that 131 newtons are moving east and 150.94 newtons is the force acting towards the north. So we're assuming that this is a northeast southwest. Yeah, we've got 41 degrees, so we have a bearing there. Similar one, this is a displacement vector. So here we're talking about displacement from an origin, and we're given an angle that is south 58 degrees west. So if you moved 430 kilometers in that direction, how far east did you go and how far south did you go? Or how far west, pardon me. So just noticed a typo there. That one would be west. So we want to figure out the x component. So finding this angle inside would be 32 degrees, and then just using SOHCAHTOA that this would be cos 32 times the hypotenuse there of 430. So we get that we've got 364 kilometers in the west direction, and then using sine, of course, for that opposite side, we get 430 times sine 32, which is 227 kilometers south. So we know the total distance that they've gone and the direction. We can summarize that as some distance west and some distance south. Last one, I think, for this video. This is with a velocity. So how much of the velocity is moving south and how much is going east? So what's our velocity in the east direction and what's our velocity in the south direction? Again, we want to just break this into components. We need to think about what the angle would be inside the triangle. So that's a 55 degrees. And looking at the east, that's going to be the adjacent. So I'm using cos. So 900, which is your total velocity, times cos 55, gives us a velocity of 516.2 to the east. And the vertical going south, we've got our opposite side. So sine 55 times 900 gives us 737.2 south. So we can break this up, and sometimes it is really important to know how much of a quantity is moving in kind of the X or Y, whether that means horizontal, vertical, north or east, all of those different kinds of directions, and breaking those up into smaller components.